The last method that we're going to use to calculate enthalpy changes in this chapter is using bond dissociation energies. So bond dissociation energy. And bond dissociation energy honestly is just as it sounds. It's the amount of energy needed to dissociate a bond. So if you're going to break a bond, how much energy do you need to break that bond? And different types of bonds take a different amount of energy. If I was to break a bond between hydrogen and fluorine, it actually takes more energy than if I was to break a bond between hydrogen and bromine. A carbon-carbon double bond is going to take more energy than a carbon-carbon single bond. So different types of bonds have different bond dissociation energies. Our abbreviation that I learned is a D, so I use this a lot, but the periodic table has our equation on the back of it, and it is using BE. So do watch out for that. If you're looking up other sources, D seems to be a pretty common abbreviation for it. BE is how your periodic table is listing it. So I'm going to use BE, but again, if you look these values up, often D is being used instead. So either one of those abbreviations work. So again, it's the amount of energy needed to break, and then specifically as a covalent bond. There is energy associated with ionic bonds, and it would be called lattice energy. It's actually a different type of energy, same sort of concept though. The amount of energy needed to break that bond. So the amount of energy needed to break a covalent bond, which is the same amount of energy that's released when you form that bond. So if you were to break a chlorine-chlorine bond, it actually takes 243 kilojoules per mole. If I was to form a chlorine-chlorine bond, it's actually going to release 243 kilojoules per mole. So if you want, you can think about it as the amount of energy released when a covalent bond forms. You would just have to switch the sign on your value. And then remember, different types of bonds take different amounts of energy or release different amounts of energy if you're looking at it from the other perspective. So different types of bonds take different amounts of energy. And again, we're going to use it to calculate our enthalpy change for our reaction. So just like we did with heats of formation, I'm just going to give us an example and then we'll go through our calculation. Maybe I'll just give us the formula first. It's actually going to be very similar to the formula that we used for calculating heats of formation, but we're going to use bond dissociation energies instead of heats of formation. And instead of doing products minus reactant, I'm going to do bonds broken minus bonds formed. So it's going to be the sum. So again, that sum symbol, and then I actually don't need the N this time. We'll do our bond dissociation energy for our bonds that are being broken. And on your periodic table, it actually says reactants instead of bonds broken. I like to think about it as broken instead. But the reactants, you are breaking those bonds, right? When you go from reactants to products, you're breaking bonds on the reactant side. And then you're forming bonds on the product side. So sum of my bond dissociation energies for my bonds formed. And again, it's the products that you're forming bonds. I always think of it as broken versus formed. When I go through the problem, I do it that way. But again, on your table, it's saying reactants and products. If it works for you to remember it that way, then that's fine. So our example, I have 2 ammonia, and I'm reacting it with 2 chlorine to produce N2H4 plus 2 HCl's. And the bond dissociation energies would be provided, just like we did with those standard heats of formation. I gave you, the compound, and I gave you its corresponding value in a table. I would do the same thing here. I would give you a particular bond, and I would give you the corresponding bond dissociation energy. However, before I do that, I want to go through and have us make a list of what's formed and broken, because once I give you the list, it kind of gives away the answer a little bit. So what I'm going to do is I'm going to actually draw them, because NH3, I don't know what I'm breaking if I don't know how they're connected, right? If I think that all three hydrogens are attached to each other, then I think maybe I'm breaking hydrogen-hydrogen bonds, but those hydrogens are actually bonded to nitrogen, so I'm not doing that. So I'm going to draw them out. So I have ammonia, and this is good practice too. Remember, the final is cumulative, so there is Lewis dot structures on there, and I'm actually going to draw the geometry as we do it. So this guy's trigonal, pyramidal. I actually have two of them, so I'm going to draw two of them, because I'm going to need the total number of bonds that we're breaking. So I'm going to draw two of them. If you can do it without drawing it out, by all means, go for it. I just think it's going to be easier to see it if we draw it out. I have one chlorine. So chlorine is just a single bond between them. There's 3 lone pairs on those if you were to draw the Lewis structure. N2H4. We haven't drawn a lot where I have 2 central atoms, but we do know that I can't have more than 2 electrons on hydrogen. Remember, a single bond is 2 electrons, so I can never have more than 1 bond on hydrogen. So hydrogen can't go in the middle, which means the two nitrogens must be bonded to each other. And then I just put the hydrogens on symmetrically. I would know that the nitrogens have to go in the middle, and then I have 4 hydrogens. I would do 2 on each. And then HCl is just a single bond between hydrogen and chlorine. And I have 2 of them, so I'm going to draw 2 of them. So what we're going to do is we're going to make a list of bonds that we're breaking. And then I'm going to make a list of bonds that we're forming, and then once we have that list, I'll give you the numbers. So bonds that are breaking, these are the things that I have on my reactant side that I don't have on my product side. So if I look at my reactant side, I actually have 6 bonds between nitrogen and hydrogen, right? 1 here, 2, 3, 4, 5, 6. So I have 6 NH bonds. If I look at my product side, I only have 4 NH bonds. So when I went from reactant to product side, I actually broke 2 bonds between nitrogen and hydrogen. Right? Things that I have on the reactant side that I don't have on the product side. What else do I have that I'm breaking? So what else do I see on the reactant side that I don't have on the product side? Yeah, good, chlorine. Hopefully you guys noticed that. I have 2 chlorines bonded to each other. On my product side, I don't have any chlorines bonded to each other. So 1 chlorine-chlorine bond is being broken. Bonds formed, these are things that I have on the product side that I didn't have on my reactant side, right? New bonds. So what am I forming? Yeah, 2 hydrogen and chlorides, right? HCl bonds. Hopefully you guys saw that. On my reactant side, I don't have any hydrogens bonded to chlorine. I have 2 of them on my product side. So we formed 2. What else? Yeah, hopefully you guys can see this one. Nitrogen and a nitrogen, and there's 1 of those. Right? I have 2 nitrogens that are bonded to each other on my product side. I don't have any nitrogens bonded to each other on my reactant side, so that's something that I formed. So the values, and again, I would provide these values, or you would get them from a table. You would have a table of bond dissociation energies, and you would look up the amount of energy associated with a nitrogen-hydrogen bond and so on. I'm just going to give you the values. These values are for 1 of them, so I am going to need to multiply it by 2 for this one, because I'm just giving you the value for 1 NH bond. Chlorine, 243. These are all going to be positive values because you have to put energy into breaking something, right? So I'm absorbing energy. If I wanted to look at the amount of energy that's released when I form them, then I would put a negative sign in front of all of them. HCl 432, and my nitrogen 240. So then we're going to do just like we did. We're going to do some of the ones that I am forming, breaking, bonds broken first, and then formed. So I have 2 nitrogen hydrogen bonds, so 2 times 390. And then I have 1 chlorine. Mathematically, you could skip that one, but if it's not 1, I just want you to see how you would do it. And then subtract from that, I have 2 HCl's, so 2 multiplied by 432. I have 1 nitrogen, so 1 times 240. All of these are in kilojoules per mole, so my units are going to come out as kilojoules per mole. So my overall enthalpy change, I'm going to grab my calculator here. And I ended up with a negative 81 kilojoules per mole. For significant digits, again, it's just digits after the decimal point because I'm adding and subtracting. None of these have any digits after the decimal point, so I don't want any in my answer. So just negative 81. And is this exothermic or endothermic? Yeah, exo. Hopefully that's what you guys are thinking. Right? I have a negative value on my enthalpy change, so I know that my final is less than my initial, right? It lost heat energy. So please do some examples, not just on this one, but some practice problems also with Hess's law and heats of formation.